Hello and welcome back in the physics class. In this video, we shall discuss about the continuous charge distribution. It is an important topic of electrostatics where charge is uniformly spread over a substance. A system of closely spaced electric charges forms a continuous charge distribution. So we have electric charges spread uniformly over a material, and this closely spaced charges forms a continuous charge distribution. Now when we talk about distribution, it can be either in one dimension or two dimensional or three dimensional. Linear charge distribution, this talks about the one dimensional distribution of charges. When the charge is uniformly distributed over a line, this line can be a straight line or a curved line. This is what we call as linear charge distribution. In the adjacent figure you can see you have a line charge, and then we will find the equation for the force. The second is surface charge distribution. When the charge is uniformly distributed over a surface, it is called as surface charge distribution. In the adjacent diagram, we can see a surface which is uniformly charged, and the study then goes. The third is volume charge distribution. This is a three-dimensional study when the charge is uniformly distributed over a volume. So these are 1, 2 and 3 dimensional study for the distribution of charge. Let us now see how we proceed to get the equation for each of these.
To derive the equation for the linear charge distribution, we have considered a wire of length L on which the charge is uniformly distributed. Q0 is a charge placed at a point R from the wire. We take a small element of wire dl, and the charge Q0 is situated at a distance R from dl. Now, we define a quantity called as the linear charge density denoted by lambda. Linear charge density is the charge per unit length. So lambda is given by Q by L. Now we are considering the small element dl, so the corresponding charge is dq, that is equals to lambda into dl. So the amount of charge present on the element dl is lambda dl. Now we have dq charge present here, and q0 is the charge placed at point. The force between these two is given by Coulomb's law, that is vector df is equal to 1 upon 4 pi epsilon naught q0 into dq divided by r square, and to give the direction we write the unit vector r. This is the small force acting due to the element dl. The total force F is equals to integral of df. So we have to integrate this equation, which is 1 upon 4 pi epsilon naught q0 dq by r square into unit vector r. This integration is taken over the complete length, so we write L. Now, we take the constants out of the integration, and our equation will be F is equals to Q0 upon 4 pi epsilon naught integral over L lambda dl, dq is substituted as lambda dl by r square unit vector r. This is the formula for the force due to linear charge distribution. Now, let us look at the surface charge distribution. This is a plane surface with uniformly distributed charges. Small area is considered of ds. Q0 is the point situated at distance r from this small area ds. Total area of the square is S. We define the quantity called as surface charge density, which is given by sigma is equals to Q upon S. It is a charge per unit area. As we did in the earlier case, we write the charge present in the small element dq is sigma into ds. It's a surface charge density multiplied by the area ds. The force acting is given by Tf is 1 upon 4 pi epsilon naught Q naught dq by r square unit vector r. Now, the net force, total force due to the complete surface would be integral of df, that is equals to integral of 1 upon 4 pi epsilon naught Q naught dq upon r square unit vector r, and this integration is taken over the surface, so we write integration over surface. Let us take the constant quantity out, that is Q naught upon 4 pi epsilon naught integral of dq. I'll write dq as sigma ds upon r square unit vector r, integration taken over the surface. So this is the equation for the force due to surface charge distribution. Now consider the volume charge distribution. This is a sphere of volume V over which charge is uniformly distributed. We consider a small element of volume dV which is located at a distance r from the charge Q naught. Here we define the volume charge density given by rho, which is equal to Q upon V. It is a charge per unit volume, what is called as the volume charge density. Now for the small volume dV, amount of charge present is dq, which is given by rho into dV. We again write the formula for small force acting due to the element dV. This is 1 upon 4 pi epsilon naught Q naught dq by r square. So you see in all the three derivations, we start with our Coulomb's law. The total force acting is given by integral of df, which is now integral of 1 upon 4 pi epsilon naught Q naught dq by r square into unit vector r, and this integration is done over the complete volume. So we take the constants out and we see that now the form is Q naught upon 4 pi epsilon naught integral of dq. I'll write dq as rho dv upon r square unit vector r, integration done over the complete volume. So these are the equations of the force due to linear charge distribution, surface charge and volume charge distribution.
So we see the important topic of charge distribution along 1, 2 and 3 dimensional, that is linear, surface and volume charge distribution. Thank you. Happy learning.